Video, we're going to find the reflection coefficient of a new load, which is a finite transmission line terminated in ZL. This slide includes a picture of this new load, which we'll call a delayed load. We're going to calculate the reflection coefficient looking into this delayed load. So we're going to calculate gamma at this spot on a transmission line. We're going to call this gamma the generalized reflection coefficient and give it the symbol gamma g. We're going to find that gamma g depends on S, the length of the transmission line on the delayed load. That fact suggests the driving point impedance of this load changes as S changes, which has applications for circuit design. This fact allows us to make impedances that would be difficult to build as lumped circuits. So we're motivated by using transmission lines to make interesting looking load impedances. Put a pin in that for now. We'll talk more about how to calculate the impedance of delayed loads soon. In the meantime, we know that gamma g of S is going to be V plus of minus st divided by V minus of minus st. But using that as the starting point for our derivation will lead us in circles because we usually calculate V minus using gamma, which we don't yet know. Instead, we're going to figure out our regular old gamma at ZL, which is gamma g of 0. Then we'll propagate the signals we use to find gamma backwards along the transmission line. We've started that strategy here by remembering the definition of gamma. There are two equations on this line, and the first one is just pointing out the cute fact that the regular old gamma we're used to is the generalized gamma with a zero-length transmission line. The second relation reminds us that gamma is the ratio of the left traveling wave to the right traveling wave at termination. We can make a quick leap to the formula for the generalized reflection coefficient. We know that the voltage at location S is going to be given by scaling our voltage at 0 by e to the propagation constant. The right traveling wave loses phase when we travel backwards by S, while the left traveling wave gains phase traveling backwards, so the propagation constant has different signs on the top and bottom of this expression. We get the final expression on the line by recognizing two things. First, the ratio of V minus of 0t and V plus of 0t still appears in this equation, and it's still equal to gamma. Second, the phases of the two exponentials add together to double the propagation constant. So our generalized reflection coefficient is given by our normal reflection coefficient scaled by twice the propagation constant along the length of the transmission line in the delayed load. Finally, we'll be looking at a lossless transmission line a lot of the time. And if we do that, gamma is equal to j times the wave number, and gamma g is revealed just to be a phase-shifted version of gamma. You might recognize this expression. A similar term appeared when we were deriving our voltage-standing wave pattern. That's because the changes in impedance we see looking into the generalized load are caused by voltage-standing wave patterns. We'll explore that very soon. In summary, delayed loads have transmission lines attached to them, and they can make interesting impedances. And the generalized reflection coefficient is a phase-shifted version of the load reflection coefficient in a lossless transmission line, and it's given by this formula at the bottom of the page.